Hey everybody, let's look at this one right here. This is problem number 2 from 1983. This is a classic one that goes from conservation of momentum to conservation of energy, or vice versa here. So we have a block of mass m is resting on a horizontal frictionless table attached to a relaxed spring of spring constant k. A second block of mass 2m right here with an initial speed of v0 collides and sticks with the first block shown right here. Develop expressions for the following quantities in terms of m, k, and v0. So first is v, the speed of the blocks immediately after the collision here. So right after they collide. So remember, anytime that you're doing a collision, use conservation of momentum. So the momentum of the system beforehand is equal to the momentum of the system afterwards there. So beforehand, we only have one thing moving. So mass times velocity is our momentum. So the first block, its mass is 2m and its velocity is v0. The second block isn't moving at all, so it has no momentum. So this is the total momentum of our system beforehand, so it's equal to the total momentum of our system afterwards. So afterwards, we have all the mass moving. So we have a total of 3m moving at this new speed that they're just calling v here. So what normally happens on these momentum problems, we have a mass on each side that cancels out, and then all we have left to do is solve for, whoops, that marker doesn't work, solve for v. So v is equal to 2/3 v0 there. So whatever this initial velocity was, 2/3 of that is our final velocity. So next part, they say solve for x, the maximum distance the spring is compressed. So this now is a conservation of energy. Strictly speaking, we had kinetic energy as the blocks were moving, and that became elastic potential energy as they compressed the spring. And the initial kinetic energy is equal to the final elastic potential there. So next line here is let's plug in for kinetic energy, 1/2 mv squared. Now right now I'm keeping the m and v generic. And then for the spring, 1/2 k x squared. This k, by the way, is a capital K for kinetic energy. This k is a lowercase k for spring constant. So the halves cancel here in that case, and then let's write our next line. Let's start to plug in. Our mass that is moving is actually 3m, and our speed here, we have to use our speed. This is which they moved off with afterwards, so that is 2/3 of v0, and all of that gets squared. And so then that is equal to k x squared there. So next up here then is let's solve for some of this. I'm going to square this side of it so that we get 3m times 2/3 squared will be 4/9 v0 squared is equal to k x squared. And now let me simplify this a little bit. This 3 I'll cancel with the 9 and make that a 3. And so I'll write 4/3 m v0 squared is, and I'll go ahead and I'm going to divide all of that by k. That's equal to x squared. And so lastly here then, I'll take the square root of each side so I can solve for x. And I'm going to go ahead and pull out, although you do not have to at all, I'm going to pull out this 4 as a 2 and this v0 squared as just v0 and write 2 v0 square root of m over 3 k. So that would be the distance that the spring is compressed. Last part here, you don't have to worry about this if we are just in the momentum chapter. We haven't covered this. If we've already done the simple harmonic motion unit, then you would know how to do this. This one's real simple. We would just simply look up the equation for the period of a spring, which is 2 pi square root of mass over spring constant. So that's a generic mass, so all we have left to do is just plug in for that mass specifically. And so it would become 2 pi square root of 3m over k.